Wowee, we've reached our first little video for section 9 or chapter 9. We talked about polynomials in class. We're going to be applying those things we learned to a couple different situations, just two. Our essential question is, how can I apply the rules of polynomials to geometric problems and real-world applications? We're going to do one example of each. Just a quick review of terminology. If we see a polynomial in standard form, remember that means that the exponents are decreasing. So maybe we have something like 3x to the fifth minus 2x squared plus 5, something like this. This is standard form because the exponents are going highest to lowest. If we had something that was a polynomial not in standard form, maybe the exponents would be going out of order. So like this guy, yes, it's a polynomial, but the exponents are out of order. And this was our original problem. You can't just switch the exponents like that. I'm just saying this was our original problem. That thing that I changed it to was bad. Okay, we had a little bit of terminology. Remember that the 3, this is called the lead coefficient. And it will help us to determine things later on down the line, maybe not even this year, maybe in Algebra 2, but lead coefficient. This 5 is the degree. Remember, the degree is the highest exponent. So since this highest exponent is 5, I would call this a 5th degree polynomial. And 5th degree polynomials are all in some ways similar to each other. So highest exponent is the degree. Finally, at the end here, we have the constant term. Again, the constant term tells us some things about the polynomial. This is a term, but the term without the exponent and the x, that's the constant term. So we see no x here. That's what makes it the constant term. Remember, it is still a polynomial term because we could think, hey, it's kind of like x to the 0, because what's anything to the 0? Oh, it's actually 1, and 5 times 1 is just 5. So if you want to, you could kind of think about it like 5x to the 0, but we know that means that there's actually no variable at all. So constant term, sweet. Okay, so first of all, let's find an expression for the perimeter of this shape. What shape, you say? I don't know, let's draw a rectangle, and it is a very happy rectangle because he's in Mr. Gregory's math video and everybody wants that. And let's say you know some things about these sides. Let's say you know, hey, this side is 2x plus 5, and maybe you know that this side happens to be x squared plus, or let's do minus x minus 3. So yeah, we have this shape, and I'm being asked to do the perimeter. Now remember, the perimeter means add up all the sides. Unfortunately, my sides, they are all expressions, and I'm not being given some piece of information like p equals 100 or something like that. So I really just have to get the perimeter as an expression, which means it'll look something like this. It'll look like a polynomial, but I won't actually be able to find x. So let's just add up all the sides. Here's the first side, 2x plus 5. Here's the second side, x squared minus x minus 3. Don't forget, though, I also need to add up this side and this side. And we know that opposite sides of a rectangle have the same measurements. So over here, I have another 2x plus 5. So that's getting added into my polynomial, 2x plus 5. Over here, I have another x squared minus x minus 3. Add that into my polynomial, x squared minus x minus 3. Okay, sweet. Now at this point, I can simplify some things, right? I can combine like terms. Remember that when we're adding polynomials together, we can combine the like terms. Combine like terms. Okay, so remember, like terms are the ones that have exactly the same like variable and exponent situation. So for example, I have two terms with an x squared. So what's 1x squared plus 1x squared? Well, that would be 2x squared. Now I need to deal with all the x's. Let's double underline them to make sure that they're different from x squares and also keep track of what I'm combining. 2x minus 1x is x plus 2x is 3x, minus x is 2x. And notice nothing's happening with the exponent. There are 2 x's. It didn't become something weird like 2x to the fourth because there were 4 x's. No, it's just 2x. Finally, I have the constant terms. So 5 minus 3 is 2, plus 5 is 7, minus 3 is 4. So here is my fully simplified, fully combining like terms polynomial. Did you like how I made like terms into a word? It's not actually. All right, finally, example 2. This will be our last example. As it turns out, you can use polynomials to model trends. And so what Major League Baseball did, that's America's baseball league, what Major League Baseball did is they said, hey, we're divided into 2 leagues. During the period between 1995 and 2001, they wanted to average the attendance. So N, this first one, is representing the attendance of the National League. And if you know nothing about baseball, that's totally fine. It's just one of the leagues. A, that's this second one, is representing the American League. And again, it's just the other league. All right, sweet. And they used polynomials to model. So N is equal to this expression. What does the t represent, though? Well, it says down here that t is the number of years after 1995. So, for example, 1995, that would be a t of 0, right? 1996, that would be a t of 1. 1997 would be a t of 2, and so on. And so they're saying if you plug this t into the expression, it will give you how many average fans were at the game. Yeah, nice. So, okay, let's look at what it's asking for. And I think this is actually a typo, which is why I awkwardly paused. It's asking for how many total games were played in 2001. I think it should be asking how many, what was the average attendance? So what was the average attendance? Or what was the attendance? Maybe it's just attendance. Okay, anyway, the point is, for 2001, let's see, this would be a t of 6. Why? Because it's years after 1995. 2001 is 6 years after 2001. Now what I could, after 1995. What I could do is I could plug t in here, and here, and here, and get 2 separate answers. But this is the chapter where we're adding 2 polynomials together, right? So let's do this. Let's add n plus a. That'll give us the total average attendance. So let's add these 2. It's kind of like when we did elimination method earlier on. I'm just combining the like terms. If we add negative 488 plus negative 318, since they're both t squares, I'm going to get negative 806 t squared. So I added the coefficients. I'm just combining like terms here. Next, let's add these 2. I think I can do this one in my head. I think it's 8,470 t. Finally, we can add the constant terms. This is another one I feel pretty confident about doing in my head. I think it'll be 50,300. Let me just think about that real quick. It seems right. Let's go with it. So what they're saying is, since I added these 2 leagues together, now what I can do is instead of plugging t6 in for t in the 2 separate ones, I can just plug 6 in for t in this total equation, and it'll give me the total attendance, not the attendance for A and N separately. So let's replace all of our t's with 6's, and I'll put it in parentheses. It's good practice, and we can put this whole expression into our calculator all in one step if you're very clever and use parentheses and enter it in literally exactly as I have here to find that the total is, let me just pause the video and find out. Okay, yeah, so I found out 72,104. It actually says that this is attendance in thousands, so really I should add 3 extra zeros here. That's a ton of attendance, and that's because Americans love their sports and they just spend money on it, and there are every single baseball team plays 162 games in a year, and that's even if they don't make the playoffs. Anyway, the point is, this is the total attendance. How did I do it? Well, I had these two separate equations, which I added together to get the total attendance, and then I just plugged in for how many years after 1995. So I plugged that T in for, 6 in for T. I'm mixing that up all day. Okay, summary, just combine like terms. Like, that's all about what this chapter is about. When you're adding two polynomials, combine like terms, and you will be a happy little stick figure. Cheers.